Okay, so next we're going to look at something called logarithmic differentiation. So in the last one I taught you nothing new. It was just an example of implicit differentiation, which we did in this unit. Thank you for reminding me. And so now we're looking at logarithmic. To explain logarithmic differentiation, I have to explain what it's not. So first off, let's look at what it's not. This is a, do you know what that's called? Okay, it's a cubic. But in terms of a function, in terms of calculus, we've called this a power function. And the derivative of power functions follow a very nice rule. That's what we started with. We can prove it. We know that's the slope of the tangent. We know that that's the rate of change. We know a lot of things about power functions. Do you know what this is called? That's an exponential function. Its derivative follows a nice set of rules, and I hope you know them. And I hope you know that ln 3 is a number. And we've spent a lot of time talking about that, but because this is a video, I'm just going to elaborate a little bit more. Ln 3 means log base e of 3 equals y. This is log form, change it to exponential. It means ln 3 is the decimal that I have to put in here so that 2.718 equals 3. It's a number. It's a decimal. We can even show that decimal on a calculator by taking 3 ln. So it's 1.09, and if I put that in as the exponent of 2.718, I'll get approximately 3. Okay, so let's be very, very clear on what that is. So that's a number. Anyway, good for us. So today's question, what do you do with this? So notice that the power function had the variable in the bottom. The exponential function had the variable in the top. And this one's messing with your head. You got a variable in the bottom and the top. Power function rule won't work. Exponential function won't work because it is neither of those. Does that make sense? That's why we can't do that. So, but interestingly enough, taking the logarithm of both sides of an equation does not disrupt the equality of the equation. You know that. You know you can take the log of both sides. You've learned this in grade 12. Now you can take the log of both sides in any base you want. Log base 3, log base 5, log base 10, which is what you're used to using, or log base e, which is what I'm used to using more often, and what you'll become more used to using. So I'm going to use log base e. In other words, I'm going to use ln. So I'm going to take the ln of both sides of this equation, and why do I choose to take the ln of it? Because I can take the derivative of that when the time comes. And I'm going to change this question to a product question. And then all that's left for me to do is for me to take the derivative of both sides. Because the derivative is, too, an operation that will not disrupt the equality. So this is how we do logarithmic differentiation. Now, I'm not done. This question's not, I just showed you how we do logarithmic differentiation. So now what I'd like to do is about 4 examples with you. Okay? I'll leave that up for a minute. Do you see how we've changed it to a product? Okay. I'm noticing most pens are stopping. I got a 1 or 2 still going. Nope, we good? Okay, so example 1. Determine y prime, or dy by dx. Same thing, right? Who cares which one we use? So, first thing I'm going to do is I'm going to take the log of both sides, and I'm choosing to take the ln. I'm going to change that to a product, just like we did. Hi. No. Are they on a lanyard?
Yeah, that's in red.
Yeah, no. Sorry. Thank you, though. So where are we? Yeah, good. So we changed it to a product, right? So we'll take the derivative of both sides. I don't expect you to write this. How do I know I'm taking it in terms of x and not y? The question asks for. So it's going to be the derivative of the first plus the times the second plus the derivative of the second times the first. And again, I don't expect you to write that unless you want to. I'll let you in on a little secret. Jazz Hands actually used Leah Bint's notation on her test to explain what she was doing. The biggest arguer I had for this notation actually used it to express her ideas. It was awesome. I was so proud. I showed my wife. It was great. So, the derivative of this will be 1 over y dy by dx. That's what you're going to forget, right? That's when I'm marking this. That's what you're going to forget, and I'm going to take 2 marks off for it. The derivative of dx by dx is 1, ln x. The derivative of ln x by dx is just 1 over x times x. Can I do this in one step and we're okay? So I had to isolate for dy by dx. How do I know I need to isolate for dy by dx? Because that's what the question told me to do. It said find y prime.
You divided by it.
Oh, I got dy by dy. That's not right. dy by dx. Sorry. Thank you, James.
Wait, so you divided by y? Right?
I actually multiplied both sides by y. No? Right? To get rid of this y. Clearing fractions. And again, this is algebra. It's not calculus. Now, the last thing that you do is you want to substitute what y is back into the equation. Because you had only x's, your equation was given in terms of x's, you don't want to leave y's here. In the last one we did with implicit differentiation, we left y's because the question had y's in it. This one, it's got a y. We know what y is in terms of x. So we're going to sub. And your final answer for this, the derivative, is x to the x ln x plus 1. And that's it. And I have to say, me talking about it probably took 20 minutes, but you doing this would take about 30 seconds. How we doing? We okay? Okay. So that's example 1, so I'll pause there.